We are recording. Okay. I'm reminded of an album by Buddy Rich where the very first song starts with a little bit of him saying something like, "Oh, yes, we are recording. We are recording. So if you don't like what you did today, then come back and re-record with us tomorrow." Buddy Rich, great jazz musician. All right, so share my screen. There we go. Let's look at this file. I've put this file in D12 for you all. Okay. So in this file, I have put some algorithms. So these algorithms are written out in a format called pseudocode, and there is an appendix in the textbook that explains how pseudocode works. So if you're not already familiar with pseudocode, and if what I explained today is not quite enough, then please go check out that appendix, and that'll answer all your questions about how pseudocode works. So first of all, what is an algorithm? An algorithm is basically just a finite sequence of instructions that tell you how to perform a procedure or solve a problem. That's all. So we are going to look at individual algorithms that are designed with a specific purpose in mind. And we're going to look at the different steps involved. And some of those steps are going to be like looping steps that will loop around sort of a maybe undetermined number of times, or perhaps it's just a determined number of times. And there's different types of loops, like a for loop and a while loop, which we're gonna look at, and then we're gonna figure out and then we're gonna see what the algorithms do, and we're gonna sort of run through the algorithm on a sample input just to see what's happening. So for the algorithms we're gonna look at today, these algorithms are designed to do something with lists. Okay, so we haven't really talked about lists yet. A list is like a finite sequence. So in mathematics, the definition of a list, that we can use here is basically a finite sequence ordered, which makes it different from a set. Okay, a set is unordered, and a set can't have repetition, but a list can potentially have repetition in it. So anybody who's familiar with Python coding, list is one of the main data types you use in Python. If you're familiar with C++, then you might want to think of this as an array. In C++, we're basically talking about arrays. Okay, so we're going to look at algorithms that do things to lists, and the things that they do are to things like searching the list to see if there is a particular number in that list, and or sorting the list, rearranging the list to be in increasing order. Those are the two types of algorithms we're going to look at: searching algorithms and sorting algorithms. Now, we're going to look at all our examples on with numbers, but you can have lists of other data types. You can have a list of strings or a list of other objects of other types, and as long as you have some way of comparing those objects, you have a way of comparing strings to say which one is, put them in order. That's a type of relation called a partial order. As long as you have or total order, as long as you have a total order defined, some sort of definition of which one should come first, like if it's alphabetical order or numerical order or so on, then you can implement these algorithms. Okay. So, like I said, we're doing it with numbers, but you could do it with other things. Now, someone, Abdullahi, you asked about what page something is on. Are you asking about the appendix, the pseudocode appendix? Yeah, that is Appendix 3 on page A11. Oh, sorry, I meant to do that to everybody. Oh. So it's near the end of the textbook, but it comes before the answers to all the odd numbers and before the suggested reading. It's directly before the suggested reading. So you can find that there. Okay, so what I'm going to do is I'm going to grab one of these and I'm going to move it over to the whiteboard. We're going to look at this first algorithm, and then we're going to go through an example of applying this algorithm to like a data input, which to a given list. So this first algorithm we'll look at is the linear search algorithm. This is the most basic type of search algorithm, pretty much, that you can use, as far as I know. It is an algorithm that just looks through the list until it finds the location of an element in the list that matches some specified number that you're searching for. And then it returns, meaning it like spits out as a sort of an output. It returns the location of that element in the list. So first of all, our list is indexed. And in computer science, usually your list or array index would start with 0. You almost always start indices at 0 in computer science, but our textbook does it differently. Our textbook starts all indices at 1. So if you are used to things starting at 0, I apologize. You're going to have to like do a little bit of mental gymnastics to remember that this book, instead of a list of length n going from 0 to n minus 1, the indices are going to go from 1 to n. So that's what we see here. So whenever you are performing an algorithm, the name of the algorithm is what's listed first. In pseudocode, it says procedure, and then the name of the algorithm. And then in parentheses, it lists what the inputs should be. So a search algorithm has 2 inputs. The first input is the thing you're searching for. That's x. So we're going to have x be an integer. When you see your inputs in pseudocode, you'll see the name of the input. That's the variable we're going to use to refer to it, and then a colon followed by a description of what that input is. This is like stating the data type of that input. So x colon an integer. Okay, so that's our first input, comma. Now our next input is going to be this list, a1 through an, a list of integers. Okay, the version in the textbook actually says that these should be distinct integers, which means different from one another, like with no repeats. I didn't include that restriction in this my version of the algorithm that I wrote up here. I just wrote it up a version that has a little more, a few more comments and that kind of thing. So what this algorithm is going to do is find the first occurrence of x in the list, if there is one. Okay. If there's more than one occurrence of x, it's not going to detect that. You could alter the algorithm if you'd like to detect multiple occurrences, but this one isn't doing that. So what does the algorithm do? The first thing the algorithm do is it introduces another index called I. So remember, an index is basically like a label. You've worked with indices before in Calculus 1 when you did Riemann sums. In Calculus 1, you use an index to label like the first term, second term, third term. You've also worked with indices back in college algebra when you studied sequences, okay, which is basically what we're doing here. The index is just the label that tells you, is it the first, second, third, fourth, ... So if the index is I, you might call it the ith term or the ith element in the list. Okay. So we introduce an index I and we initialize it with the value 1. So whenever you see this colon equals is a way of assigning a value. This is called an assignment statement. So I equals 1 is assigned the value of 1. There's 2 different uses for equals in programming. If you're not familiar with this, you can use it to mean assign the value, or you can use it to check to see if 2 things are equal. And those are kind of like different. They have different functions. An assignment statement versus a Boolean check, like is it true or false that these things are equal? So we need to distinguish between those. And so in pseudocode, I think the colon equals is used for assignment. And if you're ever going to check to see if things are equal, that is just a regular equal sign. Any questions or comments so far? This may be a little bit different than what you're used to from programming, but we all need to sort of like be on the same page so that we know how to understand notation. This is what we're going to use. Oh, I didn't even know this. Scott points out this is using an old programming format called Pascal. Oh, cool. It's created for teaching way back when. I didn't know that. That is cute. It's cool. Well, Pascal is the name of a famous mathematician, so they named it after Pascal. I can't remember what Pascal did. He was pretty cool though, as I recall. Okay, so oops, I didn't mean to do that. Any other comments or questions so far? Pascal. Yes, Pascal has a triangle named after him. Oh, that's right. That's why. Yeah. So Pascal's triangle is what we use to help us figure out binomial coefficients or like n choose k. Right? Also a unit of pressure. Yeah. One of those people who did lots of different things, like Euler. Euler did everything. Okay. So let's go on. So now that we've got our index defined, this algorithm uses a while loop. So the way that a while loop works is it essentially checks a condition, and if that condition is true, then it performs what is inside the loop. Algorithms and programming in general use this sort of indentation to sort of organize algorithms into blocks. So the interior of the while loop is all of the statements that are indented after the while statement. So we have while, and then in parentheses is a condition. If this condition is true, then we'll execute all of the statements or perform all of the things that it says to do that are in the indented section. So in this case, there's only one statement inside the loop, which is this one. So what it says is while our index I is less than or equal to n being the length of the list. Okay, we never introduced n except insofar as it's mentioned here. The n is the length of the list. Okay. If you're actually programming, you probably have to pass n into the function as an input. But this is just pseudocode, so we're a little less picky about that kind of thing. So as long as I is less than n, what we're going to do, and it was also check to see if x is not equal to ai. Ai refers to the ith element in the list. So as long as we still have not found x in the list, then we're going to make I increase by 1, which essentially is saying the while loop is looking at the ith element and saying, are you x? If no, then move to the next element. Are you x? No, move to the next element. Are you x? No, and then continue like that until the answer is yes, or we get to the end of the list, right? This condition could be false in one of two ways. Either we the I exceeds n, so we get past the end of the list, in which case we stop. Or x actually does equal ai, so we do find x, in which case, again, we stop, right? Now, after that while loop ends, then you have one of two things has happened. If your index is less than or equal to n, that means you must have found x, right? It stopped because x was equal to ai. So if your index is less than n, then you're going to define location. We're introducing a new variable. We're going to define location to be I. All right, great. Else, where the else means like if the first if was false, so this if statement is checking to see if this is true or not. Else means if the previous if statement was false, then you do this instead. So you're never going to have both of these commands executed. You're only ever going to have one or the other executed. Or if you have like a list of lots of things, you'll have exactly one of the if results executed with an else at the end. You can string together if, else, if, else, if, else, if, and then an else at the end. So you can do like 5 different things if you want to, but only one of them will happen. And so in this case, either we're going to set the location to be equal to I, which is the index of where we found the x value in the list, or we're going to set the location equal to 0, and that happens only if we never found the element. So then you return the location. So what this algorithm does is it spits out the index of where we found of the like the location in the list where we found the number x. So let's just run through this real quick with an example. Grab my notes here. feel like I'm just teaching programming now. It's like basically what I'm doing. I'm teaching programming concepts. This is like intro TSI. Run this. I should send this video to Alex and make sure I haven't made any mistakes. For the example, let's do x equals 4. So we're searching for the value 4, and let's have our list be. I'm just going to do a list of 5 numbers, and I'm going to just put them in order: 1, 2, 3, 4, 5. Okay. So what's going to happen? The very first we're going to do is set I equal to 1. Okay, so we've got I equals 1. Then we're going to start the while loop. So is 1 less than or equal to the length of our list, which is 5? Yes, 1 is less than or equal to 5. And is 4 not equal to 1? Yes. Both of those things are true, right? So this is us checking the conditions of the while loop to see if this is true. 1 is less than or equal to 5, and 4 is not equal to 1. So what we will do is redefine I to be I plus 1. What that means is you take this is the previous value of I, and then you're assigning that I plus 1 to be the new value of I. So this is kind of weird because like it's not like an equation in algebra where you try to solve for I, because that would just be 0 equals 1. Doesn't make sense. Assignment statements aren't like equations. You don't solve them. You're using a previous value of a variable to update the value of the variable to be something new. Very fundamental idea in programming. So I will be now equal to 2. Okay. So there we go. So now we have run through the while loop one time. Now we're going to check the while loop again. So this time I is 2. So is 2 less than or equal to 5? Yes. And is 4 not equal to 2? Yes. So I will be 3. And we'll keep going. 3 is less than or equal to 5. And 4 is not equal to 3. Yes, yes. So now I will equal 4. 4 is less than or equal to 5. That is true. And 4, oh, hang on. But 4 does equal 4. All right. So now this statement, x is not equal to AI, this statement is now false, right? This statement is now false. So because that statement is false, we are going to now exit the while loop. So that means that the while loop will stop, right? Because this condition is false, so it no longer is going to repeat. And so now we move on to the next statement. So the next statement is, if I is less than or equal to n, well, I is currently equal to 4, right? That was the last time we updated the value of I, was to make it equal to 4. So I being 4, 4 is indeed less than or equal to n, which is 5, right? I should have n equals 5. 4 is less than or equal to 5. So that if statement is true. So what we're going to do is set the value of location, our new variable we've introduced here. We're going to set that equal to I, which is 4. So we've set location equal to 4. Now we're not going to perform the else statement because our if condition was true, right? So we do not perform the else. So we're not going to set location equal to 0. And then so the last thing we'll do is return the location value, which is 4. And then we stop. So there we go. So that is how that works, right? What it does is it searches through the list. It searches to see if it finds X, and if it finds X, then it returns the location of X in the list. Now, question came through in the chat, which is, could we alter this algorithm so that it just returns the value of the index I after you exit the while loop? Well, I would say you could do that, except then if you didn't find X in the list, then it will return the value of n plus 1, because the I value, the I index will exceed the end of the list. You'll go past the end of the list, and then that's what will stop that's what will like cause the while loop to end, and it'll return n plus 1. That's not as that is not as I think useful, because if you were using this to program, you might want to like do a quick check to see if you found the number. And if you want to see if you found the number, all you could do is check to see if the value is 0 or not. And that's kind of handy to have a specific number that represents, no, we did not find X in the list. That's useful. And so I think that's why they introduced the variable location, and they specifically set it equal to 0 if the number was not found. I think that's good programming practice. So I wouldn't just use I. Good question. All right, so that's our first example. Any other questions about this first example? My goal here is just to show you some examples so we have some things to work with and sort of refer back to when we talk about complexity later. So the next thing I want to do is show you a binary search. Ready for binary search? Let's do it. Let's see, where's the, here it is. Okay, so now I'm going to bring binary search over. Snap that. Stick it over here. Okay, so binary search is different. What binary search does is it takes a list, it takes in an X again. It's like we're going to search for X, and it takes its list. One of the things about binary search is it is going to be a better search algorithm than linear search. It's a more sophisticated algorithm, but it has a special requirement. The list that you are searching must already be sorted. It must already be in increasing order. So here, notice this. List must be sorted in order to apply this algorithm. That's because we're going to basically be like checking to see if the number we're looking for is in the first half of the list or the second half of the list, and then cutting the list in half and repeating that process. So it relies on having a sorted list to start with. That's why we also have sorting algorithms, right? So so for doing the sorting step, which would have to have already been done before this. So here's how it's going to work. We're going to have what we call a search interval. And the search interval is going to be determined by two indices, I on the left and J on the right. So you're going to have I as your like lower bound of your search interval and J as the upper bound of your search interval. And we're going to start with the search interval being the entire list. Those are both indices on the list. It's like, what is the, yes, so we're going to start with 1 and n, because that would be the first and last term in the list, right? So then what we're going to do is we're going to do another while loop while I is less than j. So I is supposed to be on the left and j is supposed to be on the right. We're going to essentially keep on narrowing these down until I moves to the other side, right? And if you shift I up so that it becomes greater than j or equal to, right? Probably what's going to happen is you're going to make them equal, but if they ever become equal or I goes beyond j, then that is going to cause the while loop to end. Okay, so we're going to shift like this until they come together, essentially, and then it will stop. How do we do the shifting? Okay, how are we going to do this like narrowing down of the interval? Well, here's what we'll do. The first thing you do inside the while list is you define the midpoint of the list. The midpoint of the search interval. Now, say your search interval goes from like 1 to 10. Normally you find a midpoint by averaging those numbers. But if you average 1 and 10, 1 plus 10 is 11, divided by 2 is 5.5. So you don't want to just average the two numbers. You want to average them and then round to an integer, because you need the index value to be an integer. M is potentially going to be a new index value. We need to check we need to like go and like check what the nth element of the list is going to be. So M, we perform this calculation, I plus j divided by 2, which takes an average of the left front first and last element. And then it does the floor function. So when you see that little bracket that has a bottom but not a top, as the floor function. It just means round down to the nearest integer. So average and then round down, basically finding the midpoint of the search interval. So then what we're going to do is we're going to look to the, we're going to basically look to see if x is greater than or less than, right, so that backwards, is x going to be greater than or less than the nth element in the list? So should our number be found above or below that midpoint? And to check that, you don't actually need to check greater and less. You only need to check one, and then the other one would be assumed. So all this does is it checks to see if x is greater than the nth element. And if it is, then what you do is you assume that then the number you're looking for is to the right. So you take your lower bound, which is I, and you set it equal to m plus 1, which is the next number. So this is redefining the lower bound, right? So that now you are looking to the right-hand side of your midpoint. Else, what you do is you set j equal to m, which is taking the upper bound, like the right-hand side of the interval, and setting that equal to m, so that you're now looking at the left half. So this if-else combination here is basically going to check, are you below or above, and then it's going to cut the list in half, and now you're either looking at the upper half or you're looking at the lower half. Okay, and then you repeat. You take that new search interval, you find its midpoint, and you do upper half or lower half, upper half or lower half, and so on. So basically, this algorithm takes a list. It finds the midpoint. It says, where is x? Oh, x is somewhere over here. So now we're going to take this as our list and find its midpoint. Where is x? Oh, x is over here. Okay, now we take this as our list and find its midpoint. Where is x? X is over here. Oh, okay, so let's take that as our thing. Where's x? Find its midpoint, and then where's x? Is it like over on this side? Okay, so then you take that as your list, find its midpoint. Where is x? Eventually, you're going to narrow it down to like the exact location of x, right? Because eventually, you're not going to be able to cut in half any longer, and I and j are going to meet each other. And then you found your location. So this diagram sort of explains the idea behind the binary search. Does that make sense? Is that cool? I think it's pretty cool. I really like binary search. Stick that over there. If the x actually equals ai, then that falls into the else category, in which case j becomes m. And I think then that will kind of happen. That'll happen over and over again. You'll be like, oh, it's in the lower bound, it's in the lower, oh, it's in the upper, it's in the upper half, it's in the upper half, it's in the upper half, until you can't cut in half any longer. So if x actually equals ai, then you're just going to go like this. Oopsie. It's going to end up going like, oh, you're here, so cut that in half, cut that in half, cut that in half, until you can't anymore, and then stop. So I think that's what ends up happening if x equals am. Did I get that right? Or you asked about AI. I'm sorry. I was talking about am. If it's AI, then I think you just do the same thing, except it would be like flipped around. Same exact idea, except reflect this. So like, how do I do that? And like that. That makes sense. Question was, what happens if if x actually equals one of the endpoints? And essentially, this happens, I believe. That's not what AI is. It's not what AI really does. At least not yet. Yeah, so let's do the example. Yeah. Okay, so let's take a list. Again, 1, 2, 3, 4, 5 is our list. Let's make x equal to 4 again. Okay, we're going to search for that. It's not a super long list, but we can still do this. So the first thing that we're going to do is set I will be 1 and j will be 5. Okay, so we have the first number and the fifth number. So 1 to 5. So our interval is going to start with the entire list. What we're going to do is calculate the m value. And it calculates m by doing this, floor of 1 plus 5 divided by 2. So it's averaging the 1 and the 5. So in this case, that is the floor of 3. And the floor of 3 is just 3. Oh, I meant to mention that in some programming languages, when you divide, it like automatically rounds down. Some programming language, the division operation like automatically makes it an integer. If you inputs are integers, it gives you an integer as an output, and it does that by doing the floor function, I believe, or truncating whatever, like truncating the decimal, and just cutting it off, which is what the floor function does. So this floor function might not be required in some programming languages, but since we're approaching this from like a math perspective, this is mathematically what we need to do. Okay, so we've taken the average. So the midpoint is 3. So what we do then is look at the question. Okay, we found our midpoint. So now is x greater than am? So am is a3, and a3 is 3, which is our third number. I just, I have ai equal to I in this example. So a3 equals 3. So the question is x greater than, x is 4. So is 4 greater than 3? Yes. 4 is greater than 3. So we're gonna perform this. We're gonna reset I to be m plus 1. We're gonna have I, and that's gonna become 4, like that. So we've reset I to be 4. Okay. So now our list is just 4 to 5. Our interval is just 4 to 5. Our search interval is now this. Our initial search interval was 1 to 5. Now our search interval is 4 to 5. So now we'll do it again. We'll calculate m again. It's going to be the floor of 4 plus 5 over 2. So that's going to be the floor of 4.5, which is 4. So now I'm going to move over here now because I'm running out of space. So now a4 equals 4, and 4 is not greater than 4. So now suddenly our if statement here is false, right? X is not greater than am any longer because now it's equal, right? So what's going to happen then is we're going to set j equal to m, and m is 4. So we're going to set j equal to 4. Now I equals 4 and j equals 4. I equals j. So that is going to cause our while loop to end because I less than j will now be false. So we will end the while loop. And then now that we've ended the while loop, now we move on to this if statement. If x equals ai, which in this case, again, it does. We found the number 4 because 4 does equal 4, which is a4. Then location equals I. Now, I equals j equals m. What should happen is I and j and m, I believe, are all equal to each other at the end. So that's why it says I is using I here as this index to check the where the location we arrived at. I think I and j and m all end up being the same when you're done. So then location will be 4, and we'll return the value 4, which is the index again of where we found the element. So we still returned 4, just like the last one did. So that is how the binary search works. Okay, that was about the same amount of work as the linear search, but if you have a very, very large list, then linear search can be very slow. Linear search goes, it's checks. Is it this one? Is it this one? Is it this one? Is it this one? Take a long time. The binary search is way faster, and it cuts it in half, and then cuts it in half, and then cuts it in half again. And what we're going to do, what I'm going to do in the next few videos is explain. First of all, I'm going to explain growth of functions, and I'm going to explain something called big O notation, which is used to measure the speed of growth. And then I'll explain how to apply that to algorithms and like measure the speed at which these algorithms will be able to compute the answer. And we'll have a way of really concretely measuring, quantifying like the fact that the binary search is faster than the linear. Okay. So I'm going to end the video now. Let's see. I'm going to stop sharing. Well, I won't actually quite, because I do want to say one more thing, which is that there was a third algorithm I wanted to do today, but I talked kind of slow and took a while. The one I wanted to do is the bubble sort. So go ahead and look over the bubble sort algorithm in the section. Okay, it is on page 208. Bubble sort on page 208 of the textbook, and section 3.1. And familiarize yourself with that one, because we are going to come back and look at that in section 3.3. Okay. Any questions?
Oh yeah, when's the homework assignments coming out?
Oh, thanks for the reminder. I'll try to do that today. Yeah, try to do that today. Other questions?
Yeah, so like the assessment 3 is due on March 3rd, right?
Oh,
I think it was 5th.
Yeah, March 5th. We have to get that out to you real fast. What was that? Somebody.
Oh, sorry. That was my brother.
Oh, no problem. Okay. Real fast. Yeah, I'll get that out to you ASAP. Other questions? Okay, cool. Great. Thanks, folks. I'm going to stop the recording.